Okay. Okay, continuing on our discussion on this introduction to the main types of stresses that we're going to see in beams and just effectively when we're looking at structural engineering problems, we're going to move on to one of the ones which we deal with a whole bunch of structural engineers, and that's bending stress. And so this video will give sort of a conceptual overview of bending stress, and in a later video, we'll go through in a lot more detail a derivation of how we come to some of these concepts and how we can do the mathematics behind it. But really, this lecture is to provide a conceptual framework for what's going on with bending stress and really how do we approach these problems. So, what I've got here is effectively a beam, and we're applying some moments here at the end on this simply supported beam. And I guess the thing which is probably most important to keep in mind is really that bending stress results from moment. So we'll just write that down. So bending stress results from moments. And, if we want to show this a little bit clearer, obviously we could draw ourselves some little free body diagrams. We'll just do them in 3 dimensions. And then we'll do basically this side and the other side. And so, if we've got some applied moment on the edge, we're going to have some, internal moment on the inside. And if we think about it, well, what this internal moment's going to do as we're pulling and bending on it is it's going to want to, well, obviously, it wants to bend our element. And in order for our element to bend, the bottom has to get longer and the top has to get shorter. And so we'll just draw that in here. All right, so if the bottom's getting longer, and then our top is getting shorter because it's in compression. Now we can use this thought around, or this concept that we're stretching the bottom and we're compressing the top when we put a moment in this direction, and really go back to thinking around, well, what is, we draw this moment, we get used to talking about it when we're doing our equilibrium equations, but a thing to just keep in mind is really that, a moment is simply just going to equal a force multiplied by a distance. And so if we have this moment here, that's really just going to equal, a force going in this direction, a force going in this direction, and some distance between the two. So, and all of a sudden what we're seeing here is, we're going from moments to forces. Well, we've got these forces in the top and these, and in the bottom, stretching and some distance of the beam depth between there. And we know that our bending stress as a result of moments. Well, can we use this concept and sort of work out, how to work out with this pushing and pulling? I mean, we've already looked at how axial stresses are derived and how they arise. Well, maybe we could use this to talk about bending stress really in terms of axial deformation and axial stress. So if we kind of redraw our cross section here, and so we'll start basically So if this is our original cross section with some moment on it, well, that's going to be equivalent to a cross section here that has a force couple. And so it'll have some force in tension, T, and it will have some force in compression, C, and then obviously there'll be some distance between the two. And these are effectively resultant forces. Say resultant forces. Resultant compression and tension forces. All right, so now if we thought, well, we've gone from moments to some some forces, and as I said, well, we've already learned how axial stress is developed, and effectively that our axial stress is just a force divided by an area. Can we think about bending in the same way? And in fact, we really can. So if we say that each fiber of this beam acts as a tiny axial element. So what do I mean by each of these fibers? So effectively, let's take this and let's just draw it out and treat it like it's a whole bundle of axial members together. So you can think of it like a bundle of straws, which we've put together here. So let's take our element here, and then let's just break it up into a series of these discrete fibers. And so each of these fibers, and they're going to go the entire length of the element, well, each of these fibers will have, some. So if I was saying these are resultant forces, well, the top is going to have, each fiber is going to have its own little compression force, and each bottom fiber will have its own tension force. All right, and again, this should make sense. We're effectively just taking this big area and we're chopping it into little areas. We know that the top has to be in compression and the bottom has to be in tension. Now, but the question is, by how much and what is the distribution of these tension and compression forces? Well, let's go back to our little drawing here and redraw it and think about it in a little bit more detail. So if we've got a beam which is being bent, as we've said, we know that the top is in compression, and that means that it's getting shorter. And here, I'll draw that one in blue for consistency. And the bottom is in tension. And, if we pull something in tension, it gets longer. Well, if the bottom's getting longer and the top's getting shorter, there has to be some point here in the middle which is undeformed. And we know this because we're not seeing like a big we're not seeing a big step in the cross section where the top gets shorter and the bottom gets longer. We're seeing this sort of this nice distribution where as we bend our element, it looks like it's consistently bending. It's not like you see a big jagged bit in the middle. So we can use this concept of bottom getting longer, top getting shorter, and the fact that we can treat our moment as just effectively a bunch of forces with some distance between the two. And then we can think, well, if we're thinking about this as a axial problem, and so if we think about it as an axial problem, we can think about, well, how does a material which is getting pulled, how does it behave? So, if we've got some axial element and we're pulling it with some tension, it will deform, some delta. And then obviously we've all seen this, so we'll just, for steel, what we can see is that, we've got some force or stress and some deflection or strain. And really what we see is that, if more force, then we have more deformation. And similarly, we can think about it the other way around. If we've got more deformation, we have more force. So if we go the further that we go along the deformation axis here, the horizontal, the more force we have. So, we know that we have the most deformation and tension at the bottom of the beam and the most deformation and compression at the top. And in the middle, there's no deformation. And so if we're treating a bending section as a whole series of these little discrete axial elements, well, we can then work out that our stress distribution for bending, if we just look at the cross section, at the middle, it'll be 0. At the top and at the bottom, it will be at a maximum. So at the bottom, it'll be in tension. And at the top, it'll be in compression. And again, that's just simply because the top is squishing most and the bottom is extending most. And so you've got your tension here and your compression side here. And then at the middle, you've got, some place where you don't have any deformation. So that's our overall, distribution of what our bending demand would be, just coming from an internal moment. Now, just like when we talked about axial stress, we worked out, well, how would we design for this? How would we set a section so that we could reduce our axial stress? And I think it's helpful to continue thinking about these beams as just a series of axial elements all stacked together when we're looking at bending. So if we think about that's maybe we would say, what is the magnitude of the stress? And so to get there, again, we're going to think about our axial analogy. And so for our axial stress, if we had some element and it had some area A and there was some applied load P, our axial stress is simply just going to be P over A. Right? So if we want to reduce down our axial stress, we need a bigger area. So bigger area equals lower stress. And so much the same as with bending, if these are all a whole series of axial members all stacked together, acting together based upon this moment, well, then it would also, make sense that, based upon the area that each of these tiny forces is acting on, well, that will be dependent upon what the stress demand is and what the magnitude of the stress is for the stress distribution, which we've just shown. So we'll just write this down just so that it's here and it's clear. So, for bending, if we want to reduce the bending stress, then we need more area where the demand is highest. So we need more cross-sectional area where the demand is highest. And so that's effectively going to be more area at the extreme fibers. So let's just draw a quick image of what I mean by that. So if we've got our, just say a rectangular cross section, which we've been looking at here, and we discretize it into, a number of different fibers. Of an axial problem, well, it's going to have some stress distribution where we've got, like we've been showing, it's going to have some tension down here at the bottom, and I'm just going to draw the compression coming in the same on the same side. So, obviously some compression and some tension coming out. But if, our demand is highest up here at the extreme fibers, so let's say we want less stress, bigger area, one way to get a bigger area is to throw more cross-section up here relative to what's here in the middle. And so this is why you'll see that, a lot of beams are shaped like I-sections, where the I-section is effectively just putting more area up here at the top of the cross-section where the demand is highest. And so, again, if we're going to just draw the stress distribution for that, we'd have our compression. You'd have some little area of the block up top here. And then in tension, and then obviously as we come through, we've got some little bit sort of left down here in the web of the eye section. But if you do the math, you'll find out that the the magnitude of this stress is going to be much smaller than the magnitude of this stress, just simply because there's more cross-sectional area here. And this is what we term our moment of inertia. And so, as I said, we're going to discuss this in a lot more detail and give a much more rigorous derivation of how we come to this. But this is effectively the overview of how bending stress comes around, and that for designing so bending design is really about optimizing this cross section. The distribution of cross-sectional area. So that's our real high-level overview of how bending stress works. And again, to recap, it's effectively, because moments are just a force times a distance, we can treat the bending moment really as a force couple in compression and tension. And so once we have that, we can then treat it as the element as a whole series of these little compressions and tensions acting on just a little axial load. And we know that if we're deforming, we're going to generate a force and a stress. And so our distribution is going to be, we form the most at the top and the bottom of the beam, or the extreme fibers. So that's where our bending stress is going to be the most. And if we want to reduce down the magnitude of this bending stress, we simply throw more area on there, analogous to how we would for an axial stress. So I hope you found that informative as a nice just sort of overview of what bending stress is. And with that, I'd like to say thanks for watching.